How's it finding a parking spot out there? Got a challenge for y'all, or is this the time of the day where it's okay? I think it's
Pretty light up there.
pretty light, okay.
The lights are-
Yeah,
I missed a class because of
entire class?
Yes.
Dang.
I could not.
That's how I felt this morning. I just simply couldn't find a spot in the student lot anywhere. It's crazy. I mean, I keep hearing that they're working on it, but what are they gonna do? Are they gonna build a parking garage? That'd be my vote.
Yeah.
But I mean, still, I'd have to make it, and that'll take time. I don't know. Then there would be like less parking in the meantime. Wow. Dang. Well, hopefully somebody's thinking about that and figuring out how this is gonna work. In the meantime, we just all get to complain about it, right, and be late for our classes. Alright, so how many of y'all did 2.1 guided notes before class today? Alright, did anything else in the folder besides that? Did some other video watching or anybody watching the old lectures? Okay, nice, nice. Yeah, keep it up. Keep it up. Talking about atoms and bonds and things like that today. So Richard Feynman said once that if we lost all of the information, all of the collective things that we've learned as humans on this planet, we lost everything. No information, no discoveries, everything was lost. We didn't know anything about anything. What would be the single most important thing for us all to know to get back to some sort of thing we could all reasonably build back from? And he said that the most important sentence we could break it all down to is everything is made of atoms. Everything's made of atoms. If we knew that, that would be a good start. And it turns out to be the case. Everything's made of atoms. So I'm made of atoms, you're made of atoms. The tables are made of atoms, everything, it's all made of atoms. Okay. And all those things that are made of atoms, we call something, we call it matter. I'm matter, those tables matter, you're matter, the chairs matter, it's all just matter. Okay. All made up of atoms. That's it, lecture's over. Everything's made up of atoms. When you think of atoms, what does that mean to you? Does that kind of like mean something inside of you? You think of yourself as like atoms. What are atoms? What does it mean to you when you think of atoms? There's little things, these little small things that we can't see. There's little solar systems, right? Solar systems with some stuff in the middle and then things going around that stuff in the middle. Is that what atoms are? It's a start, I guess. So atoms exist by themselves, but they also come together with other atoms and they stick together sometimes. And when they come together and they stick together, what are they doing? They're bonding, yeah, they're bonding. They're forming bonds with other atoms. So they're basically reacting with the other atoms. And then we call them something different when two atoms are put together. What do we call that? They're stuck. What do you think? What do you think back there? No, no, okay. Call them molecules, right? Stick two atoms together, you get a molecule. Okay. So right here, we have an atom on the left side here. Looks kind of like helium to me. I'm not too sure, but it looks like it'd be helium. And then we have some molecules here. This is one way you can draw a molecule. That's kind of a weird way. This is another way to show you better what we're talking about here. A molecule that's made up of one carbon and four hydrogens. Yep. Okay, so we have atoms and we have molecules. Atoms and elements are kind of the same thing. We have a periodic table of elements. We have one up there. And we'll have some in the slides too. Basically elements are the names of the different atoms, and they can't be broken down into smaller substances unless you have some seriously heavy duty equipment. But for the most part, we don't break down elements into something that's smaller than them. All those that are up there on the periodic table of elements, who keeps messing with it? It keeps like drooping every semester. It's like barely staying up there. Need to get some more. So does anybody have a favorite element? You like think of your favorite element? I think we asked some favorite elements the other day, didn't we? What was your favorite?
Oh, my favorite element is gold because I can interest.
Ooh, AU, nice. That's a strange one too, right? That's not a G, it's AU. Yeah. Okay, that's cool. What's your favorite, Kate? Francium. The most expensive is francium? Didn't know that. Why is it so expensive?
This is really pretty.
Okay, what does it look like?
Grayish.
Rainbowish. Is it like safe?
Probably not.
It's okay to touch, okay. Interesting. All right, so I mean, we have lots of elements in our bodies that make up the majority of our stuff here. A lot of it's carbon and oxygen and hydrogen and nitrogen. Or as I like to call them, the honk elements. Why do I call them the honk elements? Why do I call them honk? Instead of like Chon or Notch. Because of the bonds, yeah. Because if I write them out as honk, I can write out 1, 2, 3, 4. And then I know how many bonds each of those elements or each of those atoms are going to form. That's cool. But we have to add a couple extra ones if we're talking about which ones are most essential to humans. There's also going to be a P and an S that goes with that too. Schnapps is a good way to think about all those elements if you want to use that one too. It doesn't tell you the bonds though. We got to add phosphorus, we got to add sulfur to that because those are very important elements as well. The most essential elements to humans. But there's like a bunch of other ones too. There's like 25 other ones that we need, and there's some of them over there. But yeah, basically those are the elements that come together to form covalent bonds to build up a lot of the stuff inside you. You're basically just a lot of schnapps. Honk and schnapps is all we are. For the most part. We got some other stuff floating in between too. All right, so this is the periodic table of the elements. I think it's a beautiful thing. Have you ever thought about how beautiful this thing is before? Have you ever like looked at that and thought, wow, that's a thing of beauty? Or you looked at that and kind of like get the sick feeling to your stomach, like you have to do some calculations or some molar mass stuff, right? Okay. Well, it's pretty incredible because this is the most organized way we can put it together. I mean, at least that we figured out so far. There's been like hundreds of these proposed over the past, 150 years or so. And they all look different and they're kind of cool to kind of go back and look at them. But this is the best way to do it. This is the one. This is the most recent one. Where's francium?
It's bottom cornerish.
Oh, there it is, francium. Okay, we're not going to be dealing with francium here so much, but let it be known that francium is maybe rainbow and may or may not be good for your health if you touch it. Okay, but the rest of these super organized, and we're going to see later on the lecture why this thing's so organized and how much information we can just extract just simply from looking at what column the elements are in. That's kind of a big deal. Okay, so the matter, all the stuff around us, the stuff that's made up of atoms, we can classify it in a few different ways. Elements, they're on the periodic table. Substance composed of only one type of atom. Okay, so take your pick. That's an element. Then we have molecules of an element. Talking about molecules of an element, take two oxygen atoms and stick them together. You got oxygen gas, the molecule of oxygen. Or take two hydrogens and stick them together. You got hydrogen gas. Or take two nitrogens together and stick them together. You got nitrogen gas. Okay, molecules of an element. Okay, and then we have compounds. Compounds stick two or more different elements together, and then you get a compound. Can anybody think of a compound? Like any molecule that you can just think of that has more than one type of atom in it? One type of element? What? Water, that's a good one. Water's a compound. Yeah, what were we gonna say? Sulfur? Table salt, okay, table salt, nice. Sodium and chloride, right? Awesome, okay. So I just want to pause for here, pause for a moment on the idea of compounds and molecules. Because in the real world, these are used interchangeably. They're just, people's talking about a molecule, they're talking about a compound. Somebody says the compound, they're talking about a molecule. They're like the same thing, okay? There's a fine line between the two if you really want to get all, into the details. But in this class, we're going to be using them to mean the same thing. If I have a molecule of oxygen, I'm going to have a compound of oxygen. If I have a compound of water, a molecule of water, I'm not going to like split hairs and say, well, that's not a molecule of water, that's a compound of water. That would just be, what a waste of time that would be, okay? So molecules equals compounds in my classroom. And if you meet somebody else who says, well, that professor was wrong, tell them to contact me. We'll work it out. We'll figure it out. Okay, and then there's a mixture. And a mixture is just put different things together and stir them up in a mixture, maybe put some sugar and some salt together. I don't know if that would be that good, but you could put them together and you kind of stir them together because these things dissolving in the water. But those things that you put in the water aren't actually forming bonds and coming together. The sugar doesn't actually form a bond with the sodium. It doesn't actually stick together. So that's a mixture. That's why they're different. You kind of stick things together. You put things together and they don't actually react. So that's the difference between a mixture there, or between the other things there. Okay, so back to atoms. We got to really know the atom. We got to know what the atom's made up of. Okay, and most people have heard, especially y'all, because you've all taken chemistry in order to be in here, that atoms are made up of 3 smaller particles called subatomic particles, right? Subatomic means below, like sub, like the within kind of thing. Subatomic particles. We got neutrons. Where do you find neutrons? In the nucleus of the atom. Good. Where do you find protons? Also in the nucleus of the atom. Where do you find electrons? In the orbitals. Yeah, going around like planets around the sun. About the electrons and going around the sun, it's not really like that in reality. They're not really going around in a circle. And normally I'd say, okay, I don't care, whatever. Picture them however you want because they're too small. We're never gonna have to deal with them. But we are later on going to have to come to terms with the fact that electrons are just kind of around the space around the nucleus and they're in the orbitals are around there. And it's like a probability of them being in one place versus another place. Okay. That sounds pretty crazy. That sounds pretty advanced, but they're more like this cloud here than they are this. This is like what's really happening. This isn't what really is happening. Okay. And I'll come back to that later, why I think it's important to know that. It'll be when we talk about under the concept later on. Okay, so we already knocked out where the location of the proton and neutron is. So we both know that both of those are in the nucleus of the atom. The nucleus is that central part that kind of is in the middle of the atom. If anybody that's lost anyone. The proton starts with a P, so it's got to have a positive charge. That's obvious, right? The neutron, don't like it, but the neutron has neut. It starts with neutral. So that means it has a neutral charge or no charge. Has the neutral charge. Okay, or no charge. And those are both in the nucleus, right? But the electrons, they're different. The electrons are in the orbitals, like Ashley told us, they're negatively charged. Okay, so electrons being negative is really just the other two kind of fall into place in my view on their own, but electrons, you got to remember that they're negatively charged. Right. The other thing about these is their mass. How do you think of the mass of something that's that small? I mean, you can't, it's like unimaginably small how these atoms are. They're super small. But they have mass to some degree. We typically talk about protons having the mass of 1. 1 what? Well, 1 Dalton. That's just the name we give to something that's really small but still has mass. Or you can call it AMU, which stands for, what does AMU stand for? Atomic mass unit. You got it. Okay, and two neutrons, it turns out, have the same mass, 1 Dalton or 1 atomic mass unit. Electrons are so small that we basically just say that they don't have mass, even though they have a little bit of a mass. They have a little bit of a weight to them. They're so small that we just kind of ignore that they have any weight at all when we're trying to figure out how much, when we're doing calculations, molarity calculations and things like that. Okay, so I'll let most of that will be saved for your chemistry classes, but not all of it, not all of that. We're gonna do a little bit of that next Wednesday. But I think this is a good comparison here. How big the difference in size between a proton or a neutron and an electron. Protons are about a bowling ball, and electrons are about like a penny size. Okay, so that's the difference in size between these two very, very, very small things to begin with. We got bowling balls, which are Daltons, and we got nearly zero, which are the pennies. Okay, so if we're looking at an element on the periodic table, we're typically going to see something that has a number above a letter and another number below the letter. Okay, sometimes the number is kind of off to the side, one side, sometimes just straight above. One number's above, one number's below. That's the main thing. Okay, you got some names. So this is B, this is boron with a B. The number on top is called the atomic number, the atomic number. So we got to just, when we hear that number, when we see that number on top, we have to know to ourselves, that's the atomic number. Have to know that. Okay. What information does the atomic number give us? It gives us some information. Tells us the number of protons that we have in that atom. Exactly, yeah. Tells us how many protons are in the nucleus of that atom, or just how many protons are in that atom, because that's where protons go. Excellent. It also tells us one other thing. What else does it tell us?
Number of electrons.
The number of electrons, because every time we're looking at an element in the periodic table, we're not looking at a charged version of that atom or element. We're looking at a neutral version of it. So protons, so this is going to give us the number of protons. It's also going to give us the number of electrons. Good. I'll write P plus. Oh man, my handwriting is really bad. I feel like I have to deal with that this semester. Okay. P plus and number of E minus there, not he, number. Okay. Okay. That's a good start. So is everyone okay with that so far? Does that seem like a fair thing to say? So how many protons does boron have, Isabella? 5? How many protons, how many electrons does it have? All right. It's a good start. What is this number below? This number below, what's the name of it? The atomic mass is what it's called. And we never really just deal with that number by itself. We never just say, oh, 10.81. I guess we really do sometimes. But sometimes when we want to be lazy, which is most of the time in this class with regards to that, we're just going to round it. We're going to round that to what it's closest to. What is the closest number we can round that to? 11. Okay. So the atomic mass is 11. And the mass of this thing is based upon the subatomic particles that seem to weigh anything, right? Seem to weigh anything. What are the subatomic particles that seem to have any mass at all? They have 1 Dalton as a mass. What are those two ones called, Peyton? What are those two subatomic particles called that have mass? Protons and neutrons. So that's what the atomic mass is. It's just the adding together of the protons with the neutrons. That's all that number is. So it must mean that there's a total of 11 when we add the protons and neutrons together. Okay. So how can we work backwards from that 11 number to figure out how many neutrons there are? Subtract the atomic number from the mass. You got it. Okay, so if we subtract the atomic number from the mass, we got 11. Okay, yeah, so we're taking the atomic number. I just can't say it right. Yeah. We're taking the atomic mass, which is 11, and we're going to subtract the atomic number from that. And when we do that, it's going to spit out a new number that we don't know the number of yet, which is the number of neutrons. Right? Number of neutrons. So now we have the number of protons, we have the number of electrons, easy, and we have the number of neutrons. So how many neutrons is that? 6 neutrons. Yeah, 11 minus 5 is 6. Yes, okay. Does anybody feel like uneasy about that so far? Does anybody feel uncomfortable or terrified by any of that? Okay, that's a good sign. And I mean, if that just seems like something that you kind of remember from the past and you look back at it a few times before you really remember it, that's fine too. Just do that. Make sure to make a point to do that. In the healthcare setting, a lot of times you see shorthand script for elements. And I don't love this, but this is just the way it's done. You basically flip where you put the atomic mass and the atomic number. You got this superscript that comes before the element letter, and that's your atomic mass. You got this subscript that comes before the element, and that's your atomic number. I didn't invent it. That's how it goes, though. So if you're going into healthcare after this, most of the time you're going to see elements in this form. And then if they're charged, then you'll see that in the upper right-hand corner if it's a plus or a minus, but that's not something that's usually going to be the case. All right. So just take a moment and eat right before this class. Just kind of, take a moment and let's look at chlorine and lithium. I'd like everyone in here to determine on your own the number of protons, neutrons, and electrons that chlorine and lithium have. So take yourself a moment. I'll go to another slide where you can see a periodic table on it in just 2 seconds. Those are the ones I want you to do real quick. Protons, neutrons, electrons. Okay, so where is it? Lithium is right here. And the other one is chlorine over here. You probably can't see those numbers very well. Okay, well, I'll kind of make them bigger for you a little bit. Lithium here has a 3 on top and a 6.94 on the bottom. Chlorine has a 17 on top and a 335.45 on the bottom. Okay, so take a moment. How many protons? How many neutrons? How many electrons for those two? What do you think? I don't know. I think it's if that first 4 was a 5, I'd say round up, but since it's a 4, I'd round down. So you're gonna round to the nearest whole number just with any other rounding that you do. If anybody's contemplating that. We've got another 15 seconds or so, and then we'll move on. Okay. So what'd y'all get for those? What'd you get for the number of protons and lithium, Yasmin? Oh, that's really. Yeah, you got that perfectly. I'm talking to myself here. 3 protons, 3 electrons, and then you got how many neutrons? Okay, how did you get that 4? Okay. Awesome, good. Cynthia, what did you get for chlorine? Sure. What? Well, look up here now. You can, what's well, okay, fine. We'll go somebody else. Kate, what do you want to tell us?
17 protons, 17 electrons, 18 neutrons.
Nice. How'd you get the 18? 35 minus 17 equals 18 neutrons, and then the 17 electrons, 17 protons. Nice. Okay. All right. That sounds crazy. Anybody in here? Do a couple more examples, make sure you just kind of know how to do that without thinking too hard about it. And you can do any of the other ones too. They're all there for you to do, practice on your own, and you can do a bunch of other ones too if you want. Okay, so when we draw atoms on a sheet of paper or on a tablet, we typically are drawing a Bohr diagram. It's just the easiest thing to work with when you're trying to just visualize what an atom looks like and how it can bond with other atoms, and it's just very useful. It's a good starting point, at least, until you become very used to all the atoms, and you're like Corbin, who's going to be taking using organic chemistry yet? Not yet. Okay. Well, many of you will probably take organic chemistry, I'd assume, at some point. Okay. So there's going to be electrons that exist in different orbitals around the nucleus. Okay, there's just a certain number that can fit in every orbital. Okay, so we're back to planets going around the sun. Okay, I don't love the planets going around the sun, but this is the time where it's useful. If it's ever useful, it's useful in this case. Okay. One way that I like to think about the orbitals is they are rows of seats at like a concert or something, or some show. And the nucleus is like the stage. Okay, so the seats that are closest to the stage, they fill up first. Everybody wants to be the closest to the stage, right? Right, Jaden? Yeah, okay. So this is the stage. The stage has the protons and neutrons, which are basically the performers. And then the first shell is a very, very small row of seats. It only has 2 seats. Basically can only fill up 2 electrons. Okay. Once you fill up the first 2 seats in the first orbital with 2 electrons, then you move out to the next orbital where there's 8 seats. There's 8 seats in the next orbital. Okay, so there's 2, 4, 6, 8. Okay. And then after that, how many electrons are in the third, can be in the third orbital, do you think? 8. Yeah, there's also 8 in the third. This particular element here is chlorine. So chlorine only has 7 there, but there could be 8. There could be a maximum of 8. So we got 2, 4, 6, 7 there. But the third orbital can hold up to 8, okay? We're only going to be dealing with 3 orbitals in this class. So as far as we're concerned, it's basically always 8 that can fit in any particular orbital, except for the first one. Okay. Except for the first one. Okay. So it really just has to do with the idea that chlorine has 17 electrons. Kate told us that. We have to fill them up one by one by one. And the way we're going to do that is by putting the first 2 of that 17, 17 minus 2, it's going to get us to 15 to deal with after that. But the first 2 are going to go in this first orbital here. There we go. 1, 2. Done. Okay. Now that we have 15, we're going to add 8 more of those. So we're going to subtract 8 more of those. And we're going to have 7 left over. We're going to add 1, 2, 3, 4, 5, 6, 7, 8 to the second orbital. Because that's just the max that can fit there. We can't fit 9 in there. And we're going to go to the next orbital. It'd be crazy to think that we could possibly just put 7 in there, because you got to fill up the second orbital. You got to fill up all those seats first. Okay, so now we have 7 left to deal with. We're going to put 1, 2, 3, 4, 5, 6, 7 in the third orbital. Okay. How do you feel about that? Yeah, okay with that? Okay. Okay, this is an element that's pretty important in all of life. Does anybody know what this is, just at a glance? Got 6 electrons, 6 neutrons, and 6 protons. Sorry, I think I interrupted somebody. Carbon. Oh, I think I heard over here too. Carbon. Carbon, carbon. This is carbon. Okay, so just a kind of experiment with carbon here, let's ask us what might change if we change the number of protons that carbon has. If we could somehow change the number of protons, what would be the result of that? Okay, so yeah, crazy things would happen, I guess, basically is what would happen if we change the number of protons. But the real answer to this question is the number of protons defines the element. Okay, so please silence your phones. It defines the element. Okay, so we're defining this element as having 6 protons. If we change the number of protons, we're not even talking about carbon anymore. We're just talking about something else. We're talking about something that has 7 protons or 5 protons, and those would be nitrogen and boron, for example. Okay. What if we change the number of electrons? What happens in that case? What do you think? Well, I'm looking at you. Yeah. No, you can't hide. I don't know your names yet. I don't know everybody's names yet, but you know I'm looking at you. You know who I'm talking to. Yeah, it's gonna turn ionic. You got it. Good. Yeah, it's just gonna either make it positive or negative, right? You change the number of electrons. What if you gain an electron? What charge would it have in that case? If you gain an electron, it's gonna be more negative because electrons are negative. If you lose an electron, it's gonna be, yes, you got it, exactly. Okay, it's gonna change its charge. Just for the record, it would be very extremely rare in nature to see a positive or negatively charged carbon. But it's possible for a very short amount of time. What if you change the number of neutrons? Somebody else help me out here. What if I change the number of neutrons? What's going to happen? It's going to become neutral. That's fine guess. That's fine guess. Okay, if I change the number of neutrons, we're going to be dealing with isotopes now. So there can be different versions of carbon. We still call them carbon, but they like way more because they have an extra neutron or they have 2 extra neutrons. And so that's why we have not just carbon-12, which is the normal one that we think of when we look at a periodic table, because it has an atomic mass of 12, but there's also carbon-13 and carbon-14. They're just a lot more rare to find in nature, but they exist. So just to linger on that for a second, what would change on this diagram right here if we had carbon-14? What would change there? What I need to do to fix this to make it carbon-14 over here? Yeah, I need to add 2 more neutrons there. You got it. So I add 1, 2 more neutrons. And then I got to get rid of that 6 there. I got to change that to an 8. Okay. It's a very rare form of carbon. It's not like you normally see carbon like that, but that's what you would have if you had it like that. Does that make sense? Kind of make sense? Okay. Okay, well, what are isotopes? I mean, isotopes are just atoms that have different numbers of neutrons, and there's lots of isotopes of all the different elements, not just carbon. There's different isotopes of boron and different isotopes of hydrogen and lithium and oxygen and all the other things we've talked about. There's different isotopes of them. And isotopes are the reason that we have this number, this decimal number at the bottom isn't a whole number. That's the reason it's not a whole number. Why is it 10.81? Why is it 1.01? It's just that because if you total all the different forms of that element and you average all of them together, all the atomic masses of all of them together, those are the numbers that you get. Okay, because hydrogen can exist in its very basic form with just one proton and one electron, and that's all it has with regular hydrogen most of the time. You also have this thing that's also an isotope of hydrogen called deuterium, and deuterium has a proton and a neutron. That kind of sounds weird to think that regular hydrogen doesn't have a neutron, but it doesn't. And then you have tritium that has 2 neutrons. Okay, all those are rare. Okay. I think this is a great video, but I'm not going to watch it during class. I'm going to ask you to watch it on your own time just to learn about how we know how old certain things are. It's kind of interesting to know how we can like find a mammoth bone, you know, in Alaska or in Canada and know how old that mammoth was. But we're not going to do that together right now. Okay, so we've been talking about atoms a lot, and we've brushed up against the idea of molecules, but what is a molecule? What is a molecule slash compound? What is that? Yeah, 2 atoms got stuck together, you get a molecule, okay? What holds the 2 atoms that are stuck together together? Electrons keep them stuck together. Electrons help form bonds, keep them stuck together, exactly. Okay. Bless you, yeah. What's that? Yeah, sure. When you said that, all I heard was question, but it sounded like you said bless you. Question. Okay, yeah, I got it. Yeah, bless you over there. Okay. Yeah, so here, you know, molecules form based on certain basically based on the reactivity of the atoms involved is what they form based on. Okay. And chemicals and atoms are going to be reactive with other atoms or not reactive with other atoms. In other words, they're going to form chemical bonds based on valence electrons. Valence electrons is the name that we give to the number of electrons or the electrons that are in the outermost orbital, okay? So you got like 2 that are close to the stage, 2 are close to the nucleus, pretty much with all the atoms we're going to be talking about. You have 8 after that, and then you have 8 after that, in the biggest case that we'll possibly be talking about. But really there's a maximum of 2 that can form in the first, there's a maximum of 8, and a maximum of 8 in the third. But if we only had 2 electrons in the first and 7 electrons in the second, for whatever reason, that would still mean that this one has 7 valence electrons. Okay, it would still mean that, whether they're in the second orbital or in the third orbital. If this one had 2 electrons in the first orbital, 8 electrons in the second orbital, and 7 electrons in the third orbital, then that would mean this element has 7 valence electrons. It's just how many electrons are in the outermost orbital is what we're talking about with valence electrons, okay? It actually is very important, the number of valence electrons, because that's going to determine whether or not this thing likes to form bonds with other things. If you have a full valence shell, reactions don't happen. And we call atoms that have full valence shells inert. That's the name for them when they don't react, when they don't form bonds. Inert. Okay, so take yourself a moment and look at chlorine up here on the left. How many valence electrons does chlorine have? Take a moment and count those up. What do you get? 7. Okay, good. Yeah, there's 7 up there. Okay. 1, 2, 3, 4, 5, 6, 7. Awesome. How many does sodium have? 1 valence electron. There's only 1 in the outermost orbital. Nice. Okay. So both of those without full orbitals are gonna be reactive. They're gonna be reactive. Okay. So what about neon over here? What about neon? How many valence electrons does neon have? I think I heard 8. Has 8, yeah. There's 1, 2, 3, 4, 5, 6, 7, 8. So what does that tell us about neon? What does that tell us about neon, Peyton? It's inert, yeah. It's not interested in forming bonds with anything else. It's just like get away from me, you know? But sodium, on the other hand, probably likes to form bonds with things because it only has one valence electron. Oh. Okay, sodium reactive or inert? Reactive. Is neon reactive or inert? Inert. Okay, forgot I put those little parts in there. Okay, so valence electrons. Let's get back to this amazing periodic table for a second. We can tell a lot of information from where the elements exist, what column they exist in. Okay, so group 1 elements like hydrogen and sodium, like we just saw a second ago, have one valence electron. You can tell that information just simply by looking at that column. First column, got to have one valence electron. Okay. If you go, so this is group 1 here. We got group 1. We got group 2 right here. We got group 3 over here because we skip all this stuff in the middle. We skip over there. Group 4, and then 5, and then 6, and then 7, and then 8. Group 4 elements have 4 valence electrons. 4 valence electrons. Like carbon has 4 valence electrons. That's amazing. That's amazing because that means you can form basically any kind of structure you can imagine with carbon is what that amounts to. Same thing with silicon. Heard about silicon chips before? It's what's in your smartphones, what's in your computers. You can build stuff with these things. Build anything you want with them because they have 4 valence electrons. That may not mean much to you right now, but it will mean a lot to you a couple lectures from now. And then group 7 has 7 valence electrons. You see kind of a pattern forming here? This makes so much sense. Fluorine has 7 valence electrons. Chlorine does too, and so does bromine and iodine. All these have 7. 7 valence electrons. So hydrogen, sodium, carbon, silicon, fluorine, chlorine, bromine, iodine, are these reactive or inert, do you think? They're reactive. They like to form bonds with other things. But just take a moment. Let's ask ourselves about column 8 over here. Helium, neon, argon, krypton, xenon, radon. Do you think these are going to be reactive or inert? Inert? Why do you say inert? Because they have 8 valence electrons. Yes, exactly. 8 valence electrons. So we saw neon before. We know that's not interested in interacting with anything else. Helium, same way. Argon, all these guys. You know, they have a special name. They're called the noble gases because they think they're better than all the other elements and they don't want to bond with anybody else, right? They're called the noble gases. Noble? Not Nobel, noble. Sorry. It's ironic how much of a stickler I am about spelling, isn't it, Corbin? Noble gases. Okay, I'm not a big stickler about spelling in here. Don't worry about too much. Well, within reason, but okay, what was I gonna say? That's pretty good. Well, you know what, while we're here, no, I don't want to overload you on this slide. That's fine. That's good. That's good enough. Good. No, I can't help myself. Group 7 has a very special name too, and that name is, what is group 7 called? Does anybody know what these guys are called? The halogens, yeah, just called the halogens. That sounds like a cool thing to be called, right? They're the halogens. So we got the halogens, which are right next to the noble gases, and that takes care of column 7 and 8. Yeah.
Why does it skip that huge chunk in the middle?
No, it's just the chemistry. I mean, they're, you know, there's just other, there's a lot going on there. It's a bigger conversation to open up. There's different sizes and there's different, it's just different. Have you taken chemistry? Okay, well, go to your chemistry professor, email your high school chemistry professor and tell them that you need to know more about this. Or when you take chemistry, you know, sooner when you take it again, or if you are going to take it again, then ask them about that. Or come to office hours sometime and we can talk more about it. Okay, valence electrons. We already know what valence electrons are, right? What are valence electrons? I need to hear with like a confidence from somebody who hasn't said anything yet today. What are valence electrons? Electrons in the outermost shell, exactly. Okay. So another thing to say about valence electrons is they're more stable in pairs. So if you can have twos, or basically an even number of them, more stable. Okay. So they like to be in pairs. Carbon is more stable with the even number there. Hydrogen's a little bit less stable there. Oxygen's a little bit more stable there, less stable here. They like to be in pairs, bottom line. Okay, so these unpaired valence electrons, unpaired ones. And just, you know, anytime there's some number that's not the maximum that fits in the orbital, that's going to lead to chemical bonds, Okay, so there's different types of chemical bonds. We're going to cover ionic chemical bonds. Ionic bonds are where atoms straight up lose electrons or gain electrons. Okay. Can you tell me your name back there? Can you tell me your name? Yeah. Mesa? Mesa? Okay, Mesa, can you tell me, I'll come back to you on that, Mesa. It just seemed like kind of a good question to ask you because you were already talking about that earlier. Okay, atoms lose or gain the valence electrons to become ions. So if we have sodium losing that one earlier, we were talking about earlier that looked like it could easily lose, it becomes positively charged, right? That kind of makes sense, Mesa, doesn't it? What if chlorine snatches that electron and holds onto that electron instead, fills up its octet with, because it has that 7, it wants an extra one. It's going to have an extra electron, right? That's going to make it what charged? Negatively charged. And that's how salt was born. Sodium and chlorine together, sodium chloride. It tastes good. Put it on stuff. So that's an example of an ionic bond. There's lots of other examples. And then there's covalent bonds. Covalent bonds are different because there's no giving away of electrons. There's no just like, here, I don't want this one, take it. And here, I'll take it, sure, it looks good. Covalent bonds are when they're sharing electrons. Electrons are shared. Okay, so when water molecules are formed, it's made up of hydrogen, 2 hydrogens, right, and 1 oxygen. That sound about right? Okay. That's about right? Okay. The hydrogens and the oxygen are sharing electrons. They're not giving them away to one or the other. That's why they stay together. That's one of the reasons that they stay together. So ionic bonds and covalent bonds. Okay, so we're going to talk more about those, but this is just the opening slide for that stuff. Okay, so ionic bonds. It happens when sodium with its, ooh, so unstable with this extra one here. It's just 1 valence electron. That's ugly. That's not a good thing. Okay, so it really wants to get rid of that because it's going to be really reactive and unstable until it gets rid of that. Chlorine, on the other hand, is going to be really reactive and unstable when it only has 7 valence electrons. Because the goal of every atom on the planet really is to just fill up its octet, to fill up its outer shell, to make its valence shell full. Okay, filled is what it wants to be. So it's going to be unsatisfied, it's going to be reactive, it's going to be just shaking and just unstable until it gets to have the right number that it wants. Okay? And so like this, when sodium loses that one, it becomes positive. When chlorine gains that one, it becomes negative. They're both a lot happier like that, for one, but they're also happier staying close together because sodium's actually positively charged now, right, Nisa? And chlorine is actually negatively charged now, so they just stick together, opposites attract, right? They're stuck together. Okay, so we already talked about this, but this leftmost column here, they're going to have one valence electron, so they're always going to be in the game of donating an electron. They're always going to be trying to get rid of that one. Who's going to take it? Who's going to want that valence electron? Who's always going to want that? Somebody's always going to want that. Some group, some column on the periodic table is always going to want that. Who's going to want it, Jaden? The 7 column. What do we call that column? The halogens. Nice. Always. They're going to be like, yeah, I'll take it. I'll take it. Exactly. Okay, so the halogens want it. The first column doesn't want it. So that's how they form these ionic bonds. That's that. Sodium chloride, lithium bromide, potassium chloride, any of those. Okay. So this is just the same thing. We've been dancing around this the whole time. Sodium gives up that electron, gives up to chlorine. Chlorine has a spot for it. It's happy to take it. And then once they're together, they're together. I think sometimes the thing that trips students up a little bit is just this like, what does an ionic bond look like? How do you denote an ionic bond? You just kind of write sodium and chlorine next to each other. Sodium, kind of in this shorthand, sodium and chloride. Okay, that's the ionic bond between sodium and chloride. Did I kind of just slip the fast one on y'all there? Because I mean, chlorine gets a new name when it becomes charged. It becomes chloride. That's just a convention. Okay, I didn't invent it, but we're probably pretty used to the "ide" at the end. Maybe we've heard that before. Maybe we've heard that before. Okay, so that's an ionic bond. Okay, in order to form ionic bonds, we need to have ions. Kind of makes sense, right? If we want to categorize ions based on being positive or negative, we give them a special name. We give a positively charged ion the name of a cat. We call it a cat. Or more specifically, a cation. I like to think of cation as a word that has a T in it. And the T looks like a plus sign. So cations are positively charged, like sodium. And with anion, you're on your own. I don't have a trick for this one. But I have heard somebody say an onion is negatively, it's kind of negative. But like, I like onions, so. The Grinch eats onions too. Is there a correlation between grumpiness and eating onions though? No? Okay. Because I mean, that might be objectively true. Okay, fair enough. Okay, so having onion, so we're sticking with that then. Having onion breath is negative. So anion looks a lot more like onion than cation does, so that's going to be negatively charged. Yep, ionic bonds, just two positively or negatively charged things sticking together because opposites attract. We're okay with the idea that like a positive is attracted to a negative, right? Okay with that? Okay. Looked very defensive when I said that. But no offense. I just want to make sure.
Would you multiply positive and negative because of negative and so on? So when you said those, yeah.
Yeah, duh.
Because people are you.
Okay. Okay, you make me nervous there.
Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide? Please pause the lesson and resume when you are done.
Nah.
Magnesium transfers its two valence electrons to oxygen, forming the magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine.
Okay, I think
Calcium.
that's good enough. Is that good enough? Okay with that? Okay. I might not run out of time today. Okay, so that's ionic bonds for us. Ionic bonds. We're moving on to a different kind of bond. Covalent bonds. Covalent bonds. So co, like cooperative, like coming together. Valent, so talking about the valence shells. Bonds, so you're bringing two valence shells together and they're bonding, they're sharing electrons. Okay, if you have one hydrogen atom, which has one valence electron, and another hydrogen atom, which has another valence electron, they're both very reactive by themselves because they don't have a full valence shell. But if they come together, which they're going to love to, they're going to form a bond, which is denoted by this line between the hydrogen atoms, or by just showing that there's two valence electrons coming together in the middle there. Okay. So we have a covalent bond is when the electrons are being shared between the two hydrogens. So hydrogen gas, this is hydrogen gas. You don't see hydrogen atoms floating around really that much in the atmosphere. I mean, you can't see them, so you don't know, but most of them are just hydrogen gas. They have a hydrogen bound to another hydrogen by a single bond. And a single bond is just a bond that has two electrons holding it together. Okay, we can look at this in a few different ways. We can look at the electron model, which is kind of like a Bohr diagram, pretty close. We can look at the structural formula, which has a line between the two hydrogens. And we can look at the molecular formula, which just basically tells us there's two hydrogens here. Okay. Where have you seen the molecular formula before? You've probably seen it in H2O. That's telling us there's two hydrogens there and one oxygen. The structural formula, though, is the most common thing here, and the line between it is something we eventually want to become very comfortable with. That line there is the same thing as saying there are two electrons holding these two hydrogens together. Every one line is two electrons. Okay, so when you see those lines, you're like, oh, there's two electrons. Doesn't look like two electrons, but it is. Double covalent bonds are also a thing. When we have two oxygen atoms stuck together, they form something called a double covalent bond or a double bond. And that's just when they're sharing four electrons. Four electrons are being shared between two oxygen atoms. Okay. It's drawn out like this here, an O double bond, other O. And we have a similar thing going on with carbon dioxide. Carbon dioxide here. We have a carbon in the middle, we have an oxygen on either side, and double bonds going to both of them. Okay. So hopefully that wasn't too big of a jump from single bond to double bond. Okay. We're okay? Okay. And then there's triple bonds. Triple bonds, okay, triple. So three lines between two different letters, two different atoms. Nitrogen gas is an example of classic triple bond. Okay. So if each one of those lines equals 2 electrons, how many electrons are holding these 2 nitrogens together? 6 electrons, you got it. Nitrogen gas is 2 nitrogens, which basically makes up most of the atmosphere. That's really what's out there. Not a bunch of oxygen. There's some oxygen out there, but basically just a bunch of nitrogens, what's out there. Okay, covalent bonds are strong. They're strong bonds. They're stronger than ionic bonds, actually. And there's single bonds, double bonds, triple bonds. And we already know honk 1, 2, 3, 4. We're already in good shape with that. And this slide is just saying that hydrogen forms 1 bond, oxygen forms 2 bonds, nitrogen forms 3 bonds, carbon forms 4 bonds. Honk 1, 2, 3, 4. That's a little picture from Beef, the Netflix series. Anybody seen that before? Have you heard of that? Okay. Surprising, but that's okay. All right.
When very different atoms react, like metals and nonmetals, they normally swap electrons. This is ionic bonding. But when similar atoms react, like nonmetals combining with other nonmetals, they share electrons. This is covalent bonding. Nonmetals are found on the right-hand side and upper part of the periodic table. Some common nonmetals are carbon, nitrogen, oxygen, and the halides. They have shells of electrons that are normally half or more than half full of electrons. Since they have a strong attraction for a few additional electrons, it is energetically unfavorable for them to lose electrons, so they share electrons by overlapping orbitals. This makes a bonding orbital or covalent bond that contains 2 electrons. If there is space in the outer shell, a non-metal atom can form double or triple bonds, like in oxygen or nitrogen. In the displayed formula of a compound, we represent a covalent bond with a straight line, like this.
Okay, sorry, that one's kind of loud. Okay, so I want to talk about one last bond, but in order to talk about the last bond, we need to talk about another concept first, and that concept is electronegativity. Some atoms have this special ability to really attract electrons close to themselves as part of a molecule. And so the thing I was talking about earlier about the whole cloud of electrons around the thing rather than going in orbits, this is kind of going to come into play now. It turns out that oxygen and chlorine and nitrogen and even fluorine have this really high electronegativity. So whenever they're part of a molecule, the electrons don't really stay kind of spread out around the whole molecule, but they kind of go to one side of the molecule where the oxygen and the chlorine and the nitrogen are. They kind of just spend more time over there. Okay. So if you have this negative subatomic particle that's spending more time on one side of the molecule, what's that going to do to the molecule? These negatively charged subatomic particles are just spending all their time on one side of the molecule. What's that going to do to the molecule? It's negative. And they're on one side of the molecule. What's going to happen? It's going to make it polar. Okay, so you're jumping ahead of me, but you're right. It's going to make it polar. It's going to make one side of the molecule a little bit more negatively charged is what's going to happen. That's what's going to happen. Okay. Sorry, I guess I thought the louder I said it, the more obvious the answer might be. Okay, so this brings us into this concept of polar and non-polar covalent bonds. So polar covalent bonds are the type of bonds between one atom and another atom where the sharing of electrons is unequal. The electrons spend more time on one side of the molecule. They're spending more time over here. We'll just say over here is where the electrons are spending more of the time in a polar covalent bond. Okay, makes it a little bit negative on that side. In a non-polar covalent bond, they don't spend more time on one side of the molecule. They just spend time kind of spread nicely all around the entire molecule. Okay, so they're kind of just spread out. Okay, that's the difference between polar and non-polar covalent. Polar, poles of the planet. Okay, something else with poles. What's something else that's polar I can talk about? Polar. North and South poles. Thank you. Okay, yes. North and South poles. That's it. The only poles we know. Okay. But yes, basically, there's a side that has more of something going on than the other side. Okay, that's something that is polar. Okay. Non-polar, it's equal. Okay. So because certain atoms are electronegative, very electronegative, it means that they attract the electrons more than the other atoms. So water, a molecule like water, H2O, we've heard of H2O, right? H2O is going to have the electrons more attracted to oxygen, simply because there's this fact about oxygen, that it is just more electronegative. That's just what it is. So because it's more electronegative, it's pulling in the electrons more tightly than the hydrogens are. They're fighting for the electrons. Oxygen's winning big time because it's more electronegative. So what that ends up looking like is on this molecule over here, where all the electrons are spending more time, it's partially negative closer to the oxygen. And where the electrons are spending less time, it might be partially something else on the other side. What do you think, Cynthia? What do you think, Cynthia? Yeah. Okay. Well, if it's partially negative on one side, do you think it might be partially something else on the other side? Okay. Maybe partially positive on the other side, turns out. Okay. And the fact that water is partially negative on one side and partially positive on one side leads to basically a lot of the properties about it that make life even possible, at least in the form it currently exists in. So it's kind of amazing that water is a polar molecule like that. And it's simply because oxygen is just very electronegative. Get used to saying that big word, electronegative. Feel it. Feels kind of good. Electronegative. Oxygen is electronegative. Say it with me. Oxygen is electronegative. It's electronegative. It means that it's a bully. It means that it takes electrons and doesn't share them with other elements very much. Oxygen is electronegative. Okay. And so there's a special way to denote that oxygen is very electronegative, and it's more electronegative than hydrogen is, especially when they're part of this molecule water together. Okay, we do this little curly Q here. This little curly Q negative is going to tell you that there's partially negative charge on the oxygen side of this water molecule. And there's curly Q negative, or curly Q positive, curly Q positive on the hydrogen side of this molecule. I can see that look on your face. He's like, no way that thing's called curly Q. And you're right, it's not called curly Q. Does anybody know what that symbol is? What is it? It's a lowercase delta. Yeah, we all know delta, right? Delta is like that, but it's the lowercase version of that. It's the lowercase delta. So lowercase delta gives us the way that we draw partially negative on molecules and partially positive on molecules. Polar covalent bonds have more of the electron density on one side of that bond than the other side.
A polar molecule is one in which there is a permanent dipole, arising usually because the different atoms in the molecule have different electronegativities. The attraction by a bonded atom for the pair of electrons in a covalent bond. Let us take hydrogen chloride as an example. Hydrogen chloride is a polar molecule, as the pair of electrons in the hydrogen-chlorine bond are nearer to the chlorine atom. In other words, they tend to one pole. The chlorine atom has a stronger attraction to the electrons because it has a greater electronegativity than the hydrogen atom. We can represent the hydrogen chloride molecule as H, delta positive, and Cl, delta negative. Thus, there will be an attraction between the delta negative on the chlorine atom of one molecule and the delta positive on the hydrogen atom of a neighboring molecule. The diagram below shows the permanent dipole-dipole force between the two molecules of hydrogen chloride, indicated here by the red dashed line.
Whoa, okay, so he just introduced a whole new concept. I wasn't ready for that yet, but I guess we gotta be ready soon. Okay, so he's talking about chlorine. Chlorine's also electronegative, a lot more so than other elements, but we could say the exact same thing in that same situation with oxygen being the case there too. Okay. And he started saying like one side's gonna be attracted to another side. That's exactly where we're headed with this. Exactly where we're going next. Okay, but first we got to talk about nonpolar covalent bonds. And those are just the kind where there's just no electron density spending more time on one side of the molecule versus the other side of the molecule. It's just kind of even, nice and evenly spread out around the whole molecule. Okay, so hydrogen gas is an example. Hydrogen gas, it's just two hydrogens. They're stuck together and the electrons kind of spend equal time all around the whole thing. Same thing's true for nitrogen gas or oxygen gas. One way to think about it is, well, first of all, they're not very electronegative elements to begin with, but second of all, even being a little bit electronegative, they're still going to be pulling the electrons equally in both directions. Okay, so it's just a tug of war where the equal strength is being pulled in both directions. So the result is nobody wins. Just kind of the electrons kind of stay in the middle. Or they both win, depending how you look at it. Okay, carbon dioxide is another example of a molecule like this, where oxygen is very electronegative, pulling the electrons in this direction, oxygen's pulling it in this direction. Nobody wins. It's just a non-polar molecule because electrons can't be pulled more in one direction than the other direction. And the fact that this is non-polar actually means a lot. It's very important. The same thing is true of oxygen gas. So the most important things for, our bodies and for breathing and for, expelling is oxygen gas being nonpolar and carbon dioxide being nonpolar. Okay. Both of these are pulling electrons in either direction, and the result is electrons spend equal time everywhere around this molecule. They don't spend more time on one side than the other side. Okay. Okay, I'm seeing some unsure faces and some nods, but we're just gonna kind of be okay. We're gonna have to be okay with that. If you have any specific questions though, please spit them out or just ask me to clarify too. Okay, so all of this information leads us to the last kind of bond we need to be familiar with here, and that is a hydrogen bond, a different kind of bond. Hydrogen bonds. They're the weakest of all bonds. They're very weak, but they play a very important role in lots of things we're going to talk about this semester. They happen because we have two polar molecules that are next to each other. One of them has a partially negative charge on one side and a partially positive on the other part of the molecule. So check out these two water molecules here. We have a partial negative on this oxygen. We have a partial positive on this hydrogen. What? It's like they can't really stick together, but they can be attracted to each other. Okay, so they are, and that's a hydrogen bond that's between them. They're kind of attracted to each other by these dashed lines that are kind of perpendicular to the axis of the bond there. Okay, that is a hydrogen bond. Have you ever heard of hydrogen bonds before? Has anybody ever heard of hydrogen bond before? Okay. Okay. All right. Well, now you have. Now you've heard of them. Okay. All you need is something that's partially charged on one side and partially charged on another side. They're kind of attracted to each other. They're not stuck to each other. They're not full-on charges because that would be an ion. But these are partial charges. They're attracted to each other to some degree. And the fun thing about water is it forms 4 hydrogen bonds. And that's just a good thing to know about water. We're going to talk a lot more about water next time. But for now, Water forms 4 hydrogen bonds. It has a lot of implications when it comes to frozen water being less dense than liquid water. What happens when you freeze like a bottle of water, like a glass bottle of water? What happens? No one's ever made that silly mistake before. No one's ever frozen something that you shouldn't have frozen? It expands, yeah, it expands. Yes, if you freeze, I mean, I don't know, I don't even know where you get a glass bottle of water really for the most part, but if you freeze like, what's something that somebody might freeze that shouldn't, that's mainly made of water? Forget it, okay. I froze a glass bottle of water. I found a glass bottle, it's really fancy water, and I froze it, okay? What happened is when you stick it in the freezer, the water expands. Water gets bigger when it's frozen. And it does that because of some things we're going to talk about next time. That's why it does that. I just want to just get into it, but I can't. It's not the right time. But I want you to get prepared next time by considering that and even trying to draw out how that could possibly be the case. Hydrogen bonds, they can form between the same or different molecules, but they have to have an electronegative atom involved. So for our purposes, that's basically oxygen and nitrogen. But if you want to, go a little bit further, fluorine and chlorine are also very electronegative. It's just that fluorine's the most electronegative. We just don't really talk about it that much. It's not that important for what we're going to be doing in this class. But nitrogen and oxygen, totally. Okay, I just absolutely can't help myself. So what we are going to do is we're all going to take a moment to draw water molecules. Okay. So I want you to draw 5 water molecules on your paper, 5 of them. I want you to draw 1 in the middle and then 1 in each corner of that centerpiece. Okay, so like that. I'm going to be doing it up here too. You don't need to be packing up yet. Plenty of time for that later. So once I have my waters like this, I guess first we want to ask ourselves, what is this line between the oxygen and the hydrogen? What is that? Yeah, what kind of bond is that? Covalent bond, good. How many electrons does that represent? 2. Nice, okay, we're on a roll there. Is there something about water that makes it a polar molecule, that makes that bond just not any covalent bond, but a polar covalent bond? It's the electronegativity of oxygen, yes. Electronegative element. Electronegative element. LMN. Alert. Electronegative element alert, okay? So if that's there, what do we have to show? We have to get some curlicues out. We have to get some, what are they called? What are they called? I don't know your name yet. I'm sorry. What are they called? What are they called? This is an electronegative element. This is serious. We got to figure this out. So what are we going to denote? We have to put some kind of symbol with that to let everybody know that this is an electronegative element. You told me a second ago. Lowercase delta, yes, lowercase delta. But since oxygen is so electronegative, and also because I'm giving you special permission, oxygen gets 2 lowercase deltas right up there, okay? This one does too. This one does too. This one does too. This one does too. All these get 2 electronegative signs. That's important. Okay, because all those partial negatives are there, those lowercase delta negatives are there, that tells us something else. Tells us something. Nisa, what does it tell us? Well, there's negatives on one side of the molecule. What's going to happen on the other side of the molecule? Yes, because the electrons, the reason this looks negative at all is because the electrons are just spending more time up there. They're just spending less time over here and less time over here. So we have to put a partial positive here, partial positive here. We got to put all these partial positives here. Got to do it. Got to do it. Has to be done. Somebody's got to do it. Okay, so once we have all those drawn in place, what do we know for sure about these water molecules? Are they going to stick to each other kind of, or are they just going to like not stick to each other at all? They're going to stick to each other based on their polarity, right? So what kind of bonds are they going to form between each one? The last kind of bond we talked about? Hydrogen bonds. Yeah, very weak bonds, but they're still going to have a bond between them. These really, really weak bonds that we kind of do like this, called hydrogen bonds. Is everybody drawing this? It's a good thing to draw. And long story short, the reason that I put the frozen, put the glass bottle of water in the freezer and it shattered is because water forms 1, 2, 3, 4 hydrogen bonds with other water molecules. 1, 2, 3, 4 hydrogen bonds. Okay. And that's going to get us, yes, Kelsey.
Partial negatives on the oxygen because it's taking 1 from each hydrogen. Is that what you're right too?
Yes. Yeah, not just because it's super electronegative. Yes, you're right. Yeah, absolutely right. Good question. So that's going to get us ready for a very exciting lecture next time. But before next time we're doing 2.2 in the textbook. Okay, which means you want to do chapter 2.2 in the guided notes before next time. You want to read that next time. You also might even want to watch the lecture before next time, because getting the good foundation to understand and enjoy really the rest of this course is by making sure these kind of things make good sense to you before we move on. Okay. Okay, it's 5:53. Let's meet in the lab at 6:03 and do our lab tonight. 6:03. See you all over there.